Hello. So today we're going to learn about exponential functions. We're going to learn how to identify them and evaluate them. We're going to learn how to graph them, and we're going to learn how to solve some real life problems that involve exponential functions. So down at the bottom here, an exponential function is a non-linear function of the form. So wait, non-linear, what does that mean? It just means the graph is not a line, and it means that it has a constant rate of change, if you remember that. That every time x went up by a certain amount, y would increase by a certain amount. So constant rate of change, and that ends up being the slope of the line, remember? So exponential functions are nonlinear. So the graph's not a line, and this is the format of them. Y equals a times b to the x. So a can't be 0, otherwise this would just be a linear function, because it would just be a horizontal line, y equals 0. B can't equal 1, because B is the base of our exponent. The key feature of an exponential function is that the variable is in the exponent, right? So we got a times b to the x. X is our variable. A and b are just going to be numbers, but x is our variable. And so if the variable is in the exponent, that's an exponential function. B is positive and it's not 1, right? It can be smaller than 1, it could be bigger than 1, it can't equal 1, and it can't be 0 or negative, right? A can be anything but 0. A can be positive or negative. B has to be positive, and then you'll see we'll get a different kind of graph for when B is between 0 and 1, and for when B is bigger than 1. And remember how with linear functions, whenever x changed by a constant amount, y would also change by a constant amount. In an exponential function, when x changes by a constant amount, y gets multiplied by a constant factor. So that's an important thing right there. The variable x, when variable x changes by a constant, the variable y is multiplied by a constant factor. So that's different than linear. With linear, it was you would add the same number every time to the y value. With an exponential function, you're multiplying the y value by the same number each time. All right, so the first thing we need to learn how to do is to be able to look at a table of values and determine whether they represent a linear function or an exponential function, or if maybe no function at all. So if we examine these tables, first we look at to make sure that we want to see how the x value is changing, right? So 0 to 1, 1 to 2, these are just going up by 1 each time. So we've got a constant change for the x value. So then let's see what's happening to the y values. So from 2 to 4, 4 to 6, 6 to 8, it looks like we're just adding 2 each time. So this would be a constant rate of change. The y value is changing by the same amount each time. It's going up by 2 each time. So this one is linear. The constant rate of change looks like addition over and over again, right? Adding 2 to the y value every time. What about on part B? The x value is still going up by 1 each time, but what's happening down here from 4 to 8, 8 to 16, 16 to 32? First it goes up by 4, then it goes up by 8, so it's not adding the same number each time, but it is actually multiplying by 2 each time. 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So this is going to be an exponential function. Because the y value has a constant it's increasing by a constant multiple or by the same factor each time. So a linear function, the output increases by the same number each time, with like adding 2 every time, and with an exponential function, your y value is getting like multiplied by the same number each time. It's getting doubled or tripled or something. Okay, so now we're going to look at the second thing to learn is how to evaluate exponential functions. So they're going to give us an exponential function, and they're going to give us an x value to evaluate the function at. So we'll go, you take the function y equals -2 times 5 to the x. To evaluate this function for when x is 3, we just plug a 3 in for x. And now we have to remember order of operations. What order do we do? -2 times 5, or we do 5 to the 3rd power first? So if you remember PEMDAS, parentheses, exponents, then multiply, divide, then add and subtract. Inside the parentheses, there's nothing to simplify. It's just a 5. So the next thing is exponent. So we need to do 5 to the 3rd power next. So 5 to the 3rd power is 5 times 5 times 5. That is 125. And -2 times 125 is -250. The one thing to remember is whenever they say evaluate, that means your answer needs to be a number, because you need to find the value at that of the function. Okay, let's look at B over here. The function they give us is y equals 3 times 0.5 to the x. And we're going to evaluate for when x is -2. Okay, so the -2 power, the negative part says do the reciprocal of the base. And so I'm gonna do a little thought bubble up here for a second. 0.5 is the same as 1/2, right? So if I'm doing 0.5 to the -2 power, that's the same as doing 1/2 to the -2 power. So, and 1/2, so I'm going to rewrite this as 3 times 1/2 to the -2 power. Because it's going to be easier for me to do the reciprocal of a fraction than to write 1 over 0.5 squared. So the negative part flips over the fraction. When you have a negative exponent, that means do the reciprocal of the base. So this is 2 over 1, which is just 2. And that makes the exponent become positive. Negative exponent means reciprocal of the base. So that's what we did from there to there. And then we got 2 squared is 4. And that is 12. Alrighty then. So the next thing we're going to look at is how to graph an exponential function. And there are a few key things to look for. These are going to be actually a little bit easier to graph than maybe what they look like. They look like they're kind of crazy. But really all you have to do, so if you look at any function, the graph of y equals a times b to the x is a vertical stretch or shrink by a factor of absolute value of a of the parent function y equals b to the x. So the a part is just, it's like it's either going to vertically stretch or shrink. If a is bigger than 1, it's going to stretch it out, make it taller. If a is smaller than 1, it's going to shrink it and make it shorter. If a is negative, the graph is below the x-axis, and if a is positive, the graph is above the x-axis. So there's a lot of information on this page that might be easier to understand if we take a look at a Desmos. So hang on just a second. Okay, let me bring up a Desmos page. Okay, so what happened to projector mode? Oh, let's call it that now. Okay, so here I have a function y equals a times b to the x, and I want you to like look at what happens to the function when I change the values of a. So if a is 1, the graph, watch what happens when I change a to 2. What if I change a to -2? What do you notice about the graph and a? Change it to -3. What if I change it to +3? What do you notice about the graph? You notice that whatever a is, whatever number a is, but that's also my y-intercept. You notice that? If I make a 5, look where my y-intercept is, 0, 5. If I make a -4, look where my y-intercept is, -4. So whatever this a number is, that's going to be your y-intercept every time. Then b, watch what happens. B, the impact that b has, let me change this to like 2. If b is bigger than 1, it just makes the exponential graph just grow higher faster. Like the bigger value b is, if I make it like 5, it just makes it grow steeper, right? If I make it like just barely bigger, so 2, if I make it just a little bit bigger than 1, like 1.1, and it's kind of shallow, right? If it equals exactly 1, then it's not a curve anymore, right? So it can't equal 1 to be an exponential. But anything bigger than 1, it's going to make it grow. It's going to make it get really, really high as x gets big. What if it's smaller than 1, like 0.5? All of a sudden, we still have the same, notice we still have the same y-intercept, but the graph goes down as x gets big now. So because what will be happening is, as x gets big, you keep multiplying by 1/2 over and over again, so your value keeps getting smaller and smaller and smaller. If b is bigger, now each time we're multiplying by 2 every time, so it doubles every time. So that's why it gets really, really, really big. And then the a value tells you whether it's above, if it's positive, it's above the x-axis. If it's negative, then the graph is below the x-axis. But the same thing happens. If b is bigger than 1, it's still, the graph still gets really far away from the x-axis as x gets big. And if it's smaller than 1, and as x gets big, it keeps getting cut smaller and smaller, so it gets closer and closer to 0. So that's kind of the information in here. See, when b is bigger than 1, the graph is going to get far away from the x-axis because you're going to keep multiplying by a number bigger than 1. And if a is negative, it's going to keep getting bigger negative. If b is between 0 and 1, you're going to keep multiplying by like a half or something, and your graph's going to get shorter and shorter and shorter. If a is positive, it's going to start really big positive and get really close to the x-axis. If a was negative, then it would start far away and get close to the x-axis. So that's like the general breakdown of how these functions look when we graph them. So let's look at an example where we graph one, and then we want to compare it to the graph of the parent function. So the parent function was, you remember it said for the graph y equals a times b to the x, the parent function is y equals b to the x. It's just take away the a, or make a 1 to make it the parent function. So the parent function for this function, for f of x, so if f of x is 4 times 2 to the x, so our a is 4, and our b equals 2. So if we just take a quick peek back at our last page of notes, we can tell kind of how our graph is supposed to look. A is positive, and b is bigger than 1. So if we look back here, when a is positive and b is bigger than 1, our graph should look something like this blue one. Right? A positive means our y-intercept is positive, so that's above the x-axis. And when b is bigger than 1, our graph gets far away from the x. Our number keeps getting bigger and bigger the bigger x gets, because we keep multiplying by b over and over again, and it's bigger than 1. So our graph should look something like this, right? It should start really close to the x-axis towards the left, go through our y-intercept, and then get really tall. So let's see this happen. So what I'm going to do is I'm going to say, all right, I already know for one thing. Oh, wait, I'm going to say our parent function. I'm just going to write what that is. It's just 2 to the x. So the parent function is really 1 times 2 to the x. So it has a y-intercept of 1. And then we can pick some x values and make like a little chart for each one to get some x and y values. And I'm going to change the color of this one to be a little bit more clear. I'll do f of x in green. Okay, so let's think about, well, let's go ahead and graph our parent function first. So let's pick some x values, like 0, 1, 2, maybe -1. And then we'll figure out what the y value or p of x value is, right? So all we have to do is we plug for when we want to find out when x is 0, we just plug a 0 in for x. So this would be 2 to the 0, which is 1. So that gives us a point 0, 1. Okay, that was our y-intercept, 0, 1. When we put a 1 in for x, it's 2 to the first power, which is 2. So that gives us the point 1, 2. When we put a 2 in for x, now we're doing 2 to the second power, which is 4. So that gives us the point 2, 4. And if we were to do, actually, let's do put in 3 right now. So if x was 3, we'd be doing 2 to the third power, which is 2 times 2 times 2, 8. So that gives us the 0.38. And if we were to do a -1, we would be doing, that would be 2 to the -1 power. The negative says do the reciprocal, so this is 1/2. So -1, 1/2. So it looks like our parent function goes like this. Hard to draw sometimes. Then on this side, it just gets really close to the x-axis. Okay, so now let's look at that's the parent function. Let's look at the function that they gave us, which is 4 times 2 to the x. So when x is 0, we're doing 4 times 2 to the 0. 2 to the 0 is 1, so this is 4 times 1, which is 4. So we get 0, 4 as a point. Over 0, up 4. And that makes sense because this is supposed to be our y-intercept, right? When x is 1, we're doing 4 times 2 to the 1. 2 to the first power is just 2. 4 times 2 is 8. So we get the 0.18. If we put it, it looks like it's growing really fast too. Our next point would be like way up here somewhere off the graph. So we need to check maybe a -1. So that would be 4 times 2 to the -1 power. 2 to the -1 power is 1/2. So this is 4 times 1/2. And half of 4 is 2. So we get the point -1, 2. And if we put in a -2 for x, we're doing 4 times 2 to the -2. 2 to the -2 would be, that would be 1/2 squared. The negative part would flip over the 2. So then 1/2 squared, 1/2 times 1/2 is 1/4. And 4 times a fourth is 1. So we get the point -2, 1. So it looks like our graph is doing a little bit of this. And so one way to look at this is to look at, to describe, okay, well, we need to describe the domain and range of f. So the domain is what x values does this cover, right? And this graph goes all the way to the left, and this arrow going up here tells you that it goes up forever and to the right forever. So the domain is all real numbers because every x value works for this function. The range, this graph never touches the x-axis and it never goes to the other side of the x-axis. All the y values are positive. So the range is all the y values greater than 0. Like this graph only exists where the y values are positive. Okay. So let's look at, we're going to look at a few more where we're graphing them and they just have different kinds of numbers and we're going to see where they end up on the graph. So let's graph this function and compare it to the graph of the parent function. Up here, to compare this to the graph of the parent function, this is a vertical stretch by a factor of 4. If you look at any x value, the green graph is 4 times taller. When x is 0, the parent graph was only 1 unit high, but our green graph was 4 units high. When x was 1, the purple graph was 2 units high. The green graph was 8 units high, 4 times higher. So the number right here, A, tells you a couple things. It tells you the y-intercept, and it tells you how many times taller than the parent graph our new graph is. So it's a vertical stretch by a factor of 4. So over here, compare the graph to the graph of the parent function, describe the domain and range. Okay, so let's just look at f of x equals negative, parentheses, 1/2 to the x. So on this one, our a value is -1, and our b is 1/2. So if our a value is -1, that means our y-intercept is supposed to be -1. I wish it would just let me draw dots instead of thinking I was trying to do something weird. Okay, so let's find some other points and graph this thing. Okay, we already know when x is 0, this is just going to be -1. What about when x is 1? We're going to be doing -1/2 to the 1. 1/2 to the first power is just 1/2, so this is just -1/2. So we got the point 1, -1/2. And if we remember with our, I'll just in purple really quick graph the parent function was like this. 2, 4, 8. Okay, so that's our parent function. Well, kind of. Actually, it's not. Our parent function would just be 1/2 to the x, and I don't want to mess with that right now. But let's just graph this guy. What about when x is 2, we're going to be doing -1/2 squared, which is -1/4. So you can tell we're getting closer and closer to the x-axis as we go to the right. So then we need to figure out what are we doing when we go to the left. So we need to pick some negative numbers. So -1. That would be -1/2 to the -1 power. 1/2 to the -1 power, the negative says to just do the reciprocal. So the negative that's out front stays out front, but the negative from the exponent flips over the 1/2. So we get the point -1, -2. And if we pick -2 for x, now we're doing -1/2 to the -2 power, which is negative. So now the negative from the in front stays in front. The negative from the exponent flips over the 1/2 to make it a 2. That makes the negative part of the exponent go away, but we still have the 2 part. So now 2 squared is 4. The negative was still out front, so -4. So that gives us the point -2, -4. And then you can see we've got our graph going that way. So the domain and range, the domain is all real numbers. And the range if you look the y values, everything is below the x-axis, so it's all the y values that are less than 0. Okay, now this one, actually, let's save this one for not tomorrow, but Wednesday. We'll do this or Thursday probably. So I'm going to stop the recording here, and I'm going to have your notes do up to example 4. So let me go ahead and stop this recording.